So Nalin, there's another problem which says that there is a non-Newtonian fluid which is a power law fluid, right? So it means a fluid where the relation between the momentum flux and the velocity gradient is in the form of nby equal to jby. We have to derive a velocity profile equation for the power law fluid, which is in a fully developed steady state laminar flow in a horizontal tube. So how we can approach for the solution?
So see, firstly it's an horizontal tube, so your gravitational force becomes zero directly.
Okay.
And now because the fluid is fully developed and steady state, so it will flow in only one direction, that is z. If we assume that direction to be z, so Vr and V theta will directly become zero.
Okay.
Then firstly you have to go with the basic shell momentum balance, and from that you will get tau, which is basically your flux. Then momentum flux, and then there is a relation given which says nby is equals to jby.
Right.
So there nby is basically your momentum flux tau rz, and jby is your velocity gradient.
Okay.
That is j times dvz by dy whole power n, and here y would be r. So tau rz is equals to j times dvz by dou r whole power n. So generally in case of Newtonian fluids,
It
that
is one, right?
n becomes 1, right?
Yeah.
So here you cannot take that n to be 1 because it is given the fluid is non-Newtonian.
Right.
So further, when you get the tau rz from shell balance, then you substitute that value of tau rz into this equation, and then you can further integrate this equation to get the velocity profile, and then you can use the boundary conditions, and then after integration you can get your velocity profile easily.
Okay, so we can use that condition given for calculating the tau, and then we have to substitute.
Exactly.
Okay.
As we saw the problem, so first we will draw a diagram of horizontal tube. We will take a center at this point, and first we will specify our directions. This is z direction, this will be our r direction, and this will be our theta direction. So first we will talk about the velocities. We can have velocity as Vr, V theta and Vz. So Vr will be 0 as end effects are neglected. V theta will be 0 as problem is symmetric about theta. Vz will be non-zero, and Vz will be a function of velocity in r direction. It is not a function of velocity in z and theta direction. This is a very important point to note down. So we write flux as this. This is the basic definition for flux. So we have flux in phi rz, phi theta z, and phi zz. Dou ij, when I and j are not equal, that becomes 0. Like I will specify it here. Dou ij is 0 if I is not equal to j, and dou ij is 1 if I is equals to j. I will write it again. Vr is 0, V theta is 0, Vz is non-zero. So phi rz becomes tau rz. This term becomes 0 because dou of rz will be 0 and Vr and Vz both are 0. So second terms also become 0, and the remaining term tau rz is 0. Phi theta z would be completely 0. As you can see, dou theta z will be 0, V theta and Vz are, V theta will be 0, so second terms become 0, and tau theta z you can write as minus mu d V theta by dz plus d Vz by d theta. And Vz is not a function in theta direction. Therefore, both these terms are 0. Phi zz will be P plus rho Vz and Pz. And for the third term, it will be minus mu dou Vz by dou Z plus dou Vz by dou Z. As Vz is not a function of Z, so this becomes 0 and this becomes 0. So what we get is phi Rz is tau Rz and phi Zz is P plus rho Vz and Vz. Now we will take a differential shell. Let me know. This is again our Z direction, this is our R direction, and this is our theta direction. This length here will be L, now we will write all the forces, all the rates basically. So all the flux multiplied by their specific cross section. So we will write rate of Z momentum at Z equal to 0. This will become phi ZZ So this is our area and this is flux. So flux multiplied by area becomes rate. This dr is very small and we can neglect this, so this eventually becomes 2 pi r n pi z z r equals 0. Basically this is pi z z. Here it comes out at pi z z at z equal to, and this is at z equal to 0. No gravitational force. Horizontal tube. Now we will apply the shell balance equation. Now we will divide by 2 pi delta r L, and then we will multiply with minus 1. So our equation will become r of pi z z equal to L minus r times pi divided by L plus r times pi z z, sorry, pi r z at r equal to r plus delta r minus r times pi r z at r equal to r divided by delta r is equals to 0. Now we know at the surface, that is z equal to 0 and z equal to L, our velocity is 0, and also the pressure won't be modified pressure. So basically when I will write capital PL, it will be equal to small pl, and capital P0 will be equal to small p0. So we can write this. This is RPL minus RP0 plus phi RZ will become tau RZ from here. Now taking differential properties, the above equation will become d by dr of r tau rz is equals to minus r d by d. So now we will integrate this equation. It becomes r tau rz is equals to dv by dz will be a constant into minus r square by 2 plus c1. Now here we will use logical boundary condition to get c1. So at r equal to 0, tau rz is finite or 0. For that, C1 has to be 0. So our equation becomes tau rz is equals to minus of dp by dz r by t. Now there is an equation of power law given in the question, which is nBy is equals to jv. nBy is our momentum flux and jvy is the velocity gradient. So we will write it as tau rz is equals to j times minus of j times d dz by dr whole power n, and this will be also minus. Now we have equation of tau rz here. We will substitute this here. So minus dp by dz r by 2 will be equal to minus j dvz by dr whole power n. This minus can cancel with this minus. So 1 by 2 dp by dz times r is equals to j dvz by dr whole power n. Now we will use some mathematics, and there is a negative sign here. So we will get here minus dvz by dr is equals to j by 2 dp by dz whole power 1 by n and r to the power 1 by n. From here we can write dvz is equals to minus j by 2 dp by dz whole power 1 by n r to the power 1 by n dr. Now we will integrate this equation. On integrating we will get dz is equals to minus j by 2 dp by dz whole power 1 by n r to the power 1 by n plus 1 divided by 1 by n plus C. Now to evaluate C2, we will use boundary condition, which is at r equal to r, our Vz is 0. Now first we can write Vz in a better manner, which is minus j by 2 dp by dz whole power 1 by n r to the power n plus 1 by n and n upon n plus 1 plus c2. Now we will put this boundary condition in the equation and we will simplify for c2. So dz becomes 0. So 0 is equals to minus j by 2 dp by dz whole power 1 by n r to the power n plus 1 by n into n upon n plus 1 plus c2. So we can say c2 is equals to j by 2 dp by dz 1 by n r to the power n plus 1 by n into n upon n plus 1. Now we will put this c2 in this equation. So we will get dz is equals to minus of j by 2 dp by dz to the power 1 by n small r to the power n plus 1 by n into n upon n plus 1 plus j by 2 dp by dz to the power 1 by n multiplied by r to the power n plus 1 by n into n upon n plus 1. Now we can take this j by 2 term and n upon n plus 1 term common from both sides. So we get j by 2 dp by dz to the power 1 by n into n upon n plus 1 r to the power n plus 1 by n minus small r to the power n plus 1 by n. So this equation will be our velocity profile. So I will repeat what I just did from the start. So our question was basically a horizontal tube. So velocity in r direction and theta direction became 0 because of end effect being neglected, and problem is symmetric about theta. Bz is not 0 but is a function of r direction. Then we calculated flux, and phi rz came out to be tau rz, and phi zz came out to be p plus rho bz into bz. Now we took a differential shell and we have shown phi zz here. Then we wrote rate of z momentum in both z direction and r direction, and we multiplied the flux with the cross sectional area, perpendicular cross sectional area to that specific flux, to get rate. And then we had no gravitational force as the tube was horizontal. Then we applied shell balance equation, which is basically force balance, and from there first we applied a boundary condition at this point after getting this equation, logical boundary condition, which basically is that at r equal to 0 some tau rz must be some finite value or 0. For any of the case c1 has to be 0. So we got tau rz as minus dp by dz r by 2. Then it was given in the question n by is equals to jby. This is basically our power law. As the fluid was non-Newtonian, the only difference is if the fluid is Newtonian, our n becomes 1. So our n is momentum flux and j is velocity gradient, and we got momentum flux from shell balance. So we substituted this momentum flux into this equation and we equated it. So eventually we reached to this equation where we had to evaluate C2, and to evaluate C2 we had a boundary condition that r equal to capital R, our Vz becomes 0, and from where we got our C2, and then we substituted that C2 into this velocity equation, and from there we got velocity, and this is a simplified velocity profile equation. Thank you.
Okay Nalin, here's another problem. Heavy oil is passed through a pipe of this much diameter. The pressure drop is given, the viscosity of the oil is given, and the density itself. The length of the pipe is also mentioned. It has two parts. We have to first derive the velocity and the momentum flux profile equation across the pipe. And secondly, we have to calculate the volumetric flow rate of the oil. So how we can approach?
So see, firstly I would like to warn you about something, that the viscosity of oil is 200 centipoise.
Right.
So be careful about the units in your calculation. Like don't use the 200 centipoise directly. And the question is pretty simple. You can take it to be a vertical pipe.
Okay, we are assuming.
Take it as a vertical section, and then you can further easily use the shell balance. And this is a very basic case. And after using the shell balance, you need to just use two boundary conditions, and after the integration you can easily get your flux profile. And then using Newton's law of viscosity, you can substitute tau is equals to minus mu dV by dx, and then you can get your velocity profile also after another integration and using one more boundary conditions. So generally, like, we either use one velocity or one flux boundary condition or two velocity boundary conditions.
Right.
So the question can be done using that. And in case of your second part, which is volumetric flow rate,
Yes.
first after getting the velocity, you need to calculate average velocity,
Mhm.
and through average velocity you can easily get the volumetric flow rate, because volumetric flow rate is nothing but average velocity into area. So you can easily solve the question using this.
So as we have discussed about the problem, now we will look into the solution of the problem. We will choose cylindrical coordinate for the problem. The direction are r, z and theta. R varies from 0 to r, capital R. Z varies from 0 to L, and theta varies from 0 to 2 pi. V theta is 0. Velocity in theta direction is 0 because the problem is symmetric. It is symmetric around the theta. VR is 0 because end effects are neglected, and also the fluid is incompressible. Vz is a function of Vr. So we have only one non-vanishing point, that is Vz, which is a function of Vr. Phi Rz will be equal to tau Rz, and other terms are 0. The other terms are 0 because delta Rz is 0, since I is not equal to j, and also Vr is 0, hence the second term is 0. This is equal to minus nu dou Vz upon dou R. Tau theta z is 0 because delta theta z is 0. The first term becomes 0 because I is not equal to j. The second term becomes 0 because v theta is 0, and the third term becomes 0, that is tau theta z becomes 0 because Vz is not a function of v theta, sorry. Vz is not a function of v theta. Phi zz is equal to p plus rho vz plus tau zz. This becomes p, and this becomes 0 because end effects are neglected, because vz is equal to 0 at surface, and tau zz becomes 0 because vz is not a function of z direction. So phi z is equal to p. We assume that pressure drop remains constant. Hence dou p by dou z is equal to delta p by L. Now pressure varies in z direction. Pressure varies in z direction. The differential thickness is in r direction, and the shell will look like this. This is r direction, this is that direction. Phi Rz move from r to phi Rz, r plus delta r. This is delta r, and phi zz at z equal to L, phi zz at z equal to 0. The surface area for different sections are at top and bottom, which is equal to 2 pi r delta r at inner and outer. At inner it will be 2 pi rl, at outer surface area will be 2 pi r plus delta r into L. We will balance the momentum, or say the rate. In and out, in minus out equal to 0, plus generation due to the gravity. This whole term become equal to 0 because there is no accumulation. Surface area into phi will give us the rate. So phi zz at z equal to 0 minus phi zz at z equal to L into area 2 pi r into delta r plus 2 pi r L surface area into phi rz at r minus phi rz at r plus delta r plus generation, that is volume into rho into g. Volume is 2 pi r rl into delta r into density into gravity equal to 0. Now we will divide the equation with 2 pi delta r l. And multiply it with minus 1 and rearrange. We get phi zz at z equal to 0 minus phi zz at z equal to L upon L into r plus rho gr, which is equal to dou of dou r into phi rz. We get this by applying the partial differential equation formula. Now we will rearrange, taking r common. Phi zz at z equal to 0 minus phi zz at z equal to L upon L minus rho g into r equal to dou of dou r phi rz. As we know that the boundary conditions are at r equal to 0, tau rz is 0, and at r equal to r, vz is c. Now we will apply the pressure formula in this. This will become as P0 minus rho G0, P0 minus rho G into 0 minus PL minus rho G into L upon L into R is equal to dou rho R of RZ. This becomes P0 minus PL upon L into R, which is equal to R tau RZ d of dr. After integrating, we get tau RZ equal to P0 minus PL upon 2L into R plus C1 into R. Logical boundary condition. Says that C1 has to be 0 because at R equal to 0, that C1 upon R terms becomes undefined. Hence C1 has to be 0 so that tau RZ becomes 0. So we get tau RZ equal to P0 minus PL upon 2L into applying Newton's law of viscosity minus mu dou Vz upon dou R is equal to P0 minus PL upon 2L into R. Boundary condition number 2, at R equal to R, capital R, Vz is 0. We will look into this after integrating the equation. After integrating the equation, we get Vz equal to P0 minus PL upon 4L into R square plus into 1 minus R upon R the whole square. C2, which we calculated by boundary condition 2, becomes C2 equal to PL minus P0 upon R square upon 4L into R square. We have substituted this C2 in this, and this is the final velocity profile equation. We have to calculate Vz, that is average velocity, to calculate the mass flow rate or the volumetric flow rate. Vz is equal to 0 to 2 pi 0 to R Vz R dr d theta upon 0 to 2 pi 0 to R dr d theta. D theta term cancel out from numerator and denominator because properties do not change in theta, as the problem is symmetric around theta. The final equation for average velocity is P0 minus PL upon 8 nu L into R square after substituting the equation of Vz and integrating the formula. Volumetric flow rate, which is equal to average velocity into area. The equation is P0 minus PL upon 8 nu L into pi R to the power 4. It is given in the problem statement that the values of the terms required for calculating volumetric flow rate are: diameter, that is 2r, is given as 5 into 5.08 into 10 to the power minus 2 meter. Delta P is given 68.958 into 10 to the power 3 Newton per meter square. Nu, that is 0.200 cp centipoise, which is equal to 0.2 Pascal second. Rho, that is density, it is given as 800 kg per meter cube, and length 3.048 meter. After substituting the values, we get volumetric flow rate as 0.958 into 10 to the power 3 into pi into R, that is 0.48 into 10 to the power minus 4 upon 2 to the power 4 upon 8 into 0.2 into 3.048. After calculating, we get volumetric flow rate as 0.0184 meter cube per second. This is the volumetric flow rate for the given problem. Summarizing the problem, we started with the Cartesian coordinate, the coordinate as cylindrical coordinate. Vertical tube, the flow is downward. V theta is 0 because the problem is symmetric. VR is 0 because the end effects are neglected and incompressible fluid. Vz is the function of VR. R varies from 0 to R, Z varies from 0 to L, theta varies from 0 to 2 pi. We find out the non-vanishing points, and the final equation which we got is this: phi zz is equal to P, phi theta z is equal to 0, and phi rz is equal to tau rz. As we assume that pressure drop remains constant, dP by dz is equal to delta P by L. The shell for the given problem is phi rz goes from r to r plus delta r. Phi zz goes from z equal to 0 to z equal to L. The surface area for the given shell is 2 pi r into delta r for top and bottom. At inner it is 2 pi r into L. At outer it is 2 pi L into r plus dr. After balancing the rate, we get to know that phi rz is equal to phi zz at z equal to 0 minus phi zz at z equal to L minus rho g upon L into r. After substituting the pressure, we got the final equation, flux profile equation. After substituting logical boundary conditions and calculating the constant, this is C1 equal to 0 because at r equal to 0 tau rz was undefined, but logical boundary condition says that tau rz is equal to 0 at r equal to 0, so C1 has to become 0. After applying Newton's law of viscosity, we calculated and the velocity profile equation. After substituting boundary condition number 2, that is at r equal to r, Vz becomes 0. We calculated C2 as the value of constant C2 and substituted it in the velocity profile equation, and this is the final velocity profile equation. We calculated average velocity equation, which we require to calculate volumetric flow rate. Volumetric flow rate is equal to average velocity into area. This is the final equation for volumetric flow rate. After substituting the given values, we calculated volumetric flow rate, which came out to be 0.0184 meter cube per second. Thank you.